So before I get into topic 6, I want to go back to this theorem about the polar equations for circles. I got really tongue-tied and I think I made it worse and worse the more I talked in the last video. So I decided to start this one by kind of explaining the 2a thing a little bit better because what you essentially have to do is just kind of like factor a 2 out of whatever your coefficient is. So what we have here is the format. We have r equals 2 times a times sine of theta, r equals negative 2 times a times sine of theta, r equals 2 times a times cosine theta, r equals negative 2 times a times cosine theta. You can read all the rest about the center and the radius. But what I was trying to say is we had the equation earlier where we had r equals 3 sine theta. We need to find a way to write this in the form 2 times a times sine of theta. So we need to find a way to take this and write it as 2 times a times sine of theta. So how on earth do we turn a 3 into a 2 times an a? You factor a 2 out. So you basically take 3, divide out a 2. Okay, so we would get r equals 2 times, well, if I take 3 and I factor a 2 out, that makes it 3 halves. So we would take 2 times 3 halves. When you multiply it, it still equals 3, but we have it in the correct format. And what we know now is this right here is our radius. And because we meet the criteria for this equation right here, we also have a center at the point 0, comma, whatever that value is. Okay. So that's what I was trying to say when I said factor out the 2 and then you want to figure out what you multiply by. But I think I said you want to figure out what you multiply by to get 3, not 2. I meant the 2. So that's what this is all about. Now, to me, I would honestly almost rather convert my equation to rectangular form and complete the square because I'm pretty good at completing the square. So I can do that honestly quicker than I can try to like remember all of this junk right here. Okay. But it's up to you. It's really cool how it works, but you're not going to be responsible for that because as you're going to see in this very next topic, we're going to look at symmetry and then we're also going to look at graphing with a calculator. Okay. So let's get to topic 6. And really, sorry for the tongue-tiedness. I think I said, what do you multiply to get a 3, not a 2? I had it all backwards. But anyway, so for topic 6, we're going to talk about symmetry and graphing with a calculator. Depending on where you go, what book you use, the situation you're in for your trig class, sometimes when you learn about symmetry, when it involves polar equations, what people will do is they will test for symmetry and then that will lead them to their equation. We're going to really focus a bit more on the technology, which is kind of exciting because when I went to UNCA, it was like calculators were not allowed. Okay. So I got my undergraduate degree at UNCA. We did like very little with technology, like almost nothing. And then I went to Western for my graduate degree, and it was like nothing but technology. So like I can kind of appreciate both sides. I can appreciate doing it by hand. I can appreciate the calculator. In a situation like this, these are a little bit cumbersome. Let's really embrace the technology here, okay? But with that said, I do want to talk very briefly about symmetry, and then we're just going to move on and learn how to use the calculator. So, it says here under topic 6, because symmetry exists with rectangular equations, it is no surprise that it also exists with polar equations. And then this should actually disappear. I copied and pasted and forgot to erase that out. Okay. So what we're going to do is we're going to look at these 3 graphs and we're going to discuss like what symmetry would mean. Okay. So describe the symmetry of each graph. So for part A, what they're doing is they're saying, hey, let's say you have this point here and you have this point here. So you have some kind of graph where you have r theta and then you have r negative theta. Okay, so that's going to always mean something. So if for every r theta you have r negative theta, that is going to indicate some kind of symmetry. For the next graph, this one's a little bit weirder, but we have r theta, and then for every r theta, if you have r comma pi minus theta, you're going to have some kind of symmetry. And then if you have r theta and negative r theta, that's going to indicate some kind of symmetry. So just really quick, let's kind of review symmetry in the rectangular world. So if we have symmetry with respect to the x-axis, we could check that pretty easily, okay? You would know that if you folded the graph along the x-axis, the 2 sides of the graph would meet. But basically what we could do is we could or I don't want to say y, we could replace, there we go. We could replace, y with negative y. And if we ended up simplifying and getting the same function back, we had symmetry with respect to the x-axis, okay? For symmetry with respect to the y-axis, what we could do is we could replace x with negative x, okay? And kind of really make that make sense in your head, okay? So let me give myself a little more room. So for this one right here, if we're looking at a graph that has symmetry with respect to the x-axis, for every point x, y, we would need the point x negative y. So you replace all your y's with negative y. And if you get the same function back, you have symmetry. Now, for symmetry with respect to the y-axis, okay, for every xy, you would have to have negative xy. Okay, so to check for symmetry with respect to the y-axis, replace your x with negative x. If you get the same function back, you have the symmetry. And then finally, we would have symmetry with respect to the origin. And you would replace x and y with negative x, negative y. And if you got the same function back, you had symmetry. So that would mean for every xy, you would need, let me do a different color. For every xy, you would need the point negative x, negative y. And so you can kind of see how you would have the different symmetries here, okay? Now, we have something very similar in the polar world, and we talked about a little bit already, but let's like really dive in, okay? So in order to have symmetry with respect to the polar axis, remember this right here, this is your polar axis. So to have symmetry with respect to the x-axis or the polar axis, we basically let theta equal negative theta. And if we get the same function back, then we've got some kind of symmetry. So I'm going to write that a little better. We're going to replace theta with negative theta. And again, if we get the same thing back, we've got the symmetry, okay? And we would say we have symmetry with respect to the polar axis, or you could say the x-axis, okay? All right. Now, in this case, this is kind of the weirdest one to check, but you have some point r theta, and we're saying, hey, if we have the point r, comma, pi minus theta, then we have symmetry with respect to this idea of theta equals pi over 2, okay? So you can basically replace theta with pi minus theta, and if you get the same thing back, then you've got symmetry with respect to pi over 2, or you could say the y-axis, okay? And then finally, we have this point here, r theta. We have the same point, which is negative r theta. And if that is the case, you can basically replace both, and then you have symmetry with respect to the pole. Okay. Now, I'm not going to go much deeper into that. Again, depending on, the instructor, the book, the school, the whatever, some people really start teaching really special types of graphs using this idea of symmetry. We're going to use the technology a bit more. We may discuss some of the symmetry as we go, but we're not going to use the symmetry to get the graph, okay? So now let's talk about graphing on your equation. So your equation can graph polar equations, which, probably isn't too surprising to you. Again, I already told you that like when I was at UNCA, we did almost nothing with technology. I mean, very little. This was also a while ago, so there was less technology freely available, but they just didn't really do a lot with technology. And then so I get my undergraduate degree there, then I don't transfer, but I get my graduate degree at Western, and it was like technology galore. They use so much technology. So I was always behind the curve because I didn't really understand the technology. And so I have a really broad appreciation for both, like doing everything like truly by hand and then doing, a lot of stuff with technology. So both super amazing. In this case, I do think with the time constraint we have in the summer and with kind of the complexity of these, it's just kind of nice to take a little bit of a breather and use your calculator to help out here. So steps for graphing polar equations on the calculator. You know how like when we're dealing with just regular rectangular equations, we always had to solve them for y to type them into our Texas Instrument TI whatever calculator. You kind of have to do the same thing here, but here you're going to solve for r. So you want to make sure your equation is solved for r. Make sure your calculator is in radians mode. And then while you're checking radians mode, you do need to put your calculator in polar mode. Okay, so I'll show you how to do all of this. Now, once you are in polar mode, you still need to check your window. So we know how to check our window for like rectangular stuff. You can check your X min, X max, you can check your X scale, you can do your Y min, your Y max, your Y scale. All that's fine. But you're also going to need to put in values for theta. So you're going to have like something theta min, theta max sort of, and then you want to also put in what they call theta step. And so you want it to be a pretty small value. So we're going to do, I think I have 1 over 2 pi. Yeah. So like right here, we're going to use 1 divided by 2 pi for our theta step. It's a good place to start. It's not mandatory, but it's just what I always do. Okay. Now, when you need to like type in your equation, you can just go to like regular old y equals, but now you're going to, instead of seeing like y1, y2, y3, you're going to have r1, r2, r3. Type in your equation. If you need to make further adjustments to your window, you can. And then sometimes our graphs, because the window is sort of rectangular and not square, we have this zoom function in our calculator called zoom square. It'll sometimes make our graphs look a little bit better, but I'll show you that when we get there. So we're going to practice first. We're going to practice r equals 1 plus cosine theta. We're going to set the x-axis, so x min, x max, we're going to set it to negative, from -3 to +3 with a scale of 1. We're going to do the same thing for the y-axis, -3 to +3 with a scale of 1. For theta, we're going to set it from -2 pi to +2 pi, and then we're going to set the theta step as 1 over 2 pi, and then we'll sketch kind of what we see below. Now, we already know that I can't do like the dual screen. Like some people have a fancier setup and they can do like dual screens. I can't do that. Or I've tried to figure out how and I don't know how. So I don't know if it's a technology thing or a Jillian thing. So we're going to switch back and forth. We don't love it, but we're tough. So we are going to graph 1 plus r, or r equals 1 plus cosine theta. Okay. So when you go to your calculator, first of all, make sure you're in radians. So my calculator tells me, hey girl, you're in radians, but let's double check. We go to mode and we want to make sure that we are in radians. And then if you go down to the fourth line, so the line directly below radians and degrees, we have function, parametric, polar. You want to highlight polar. That'll allow you to type in and graph polar equations, okay? So then when we go to the window, notice you now have theta min, theta max, theta step. So we're going to set theta min as -2 pi, so -2, and then just second caret button, pi. It's going to automatically translate it to a decimal, but don't worry about it. And then this is already 2 pi, but just to show you, 2 second caret pi. And then I'm going to set my theta step as 1 over 2 pi. You don't have to do that. You just want some kind of like fairly small value. And so this is just one place to start. So we're going to do 1 divided by, and then I'm going to go ahead and put my denominator in parentheses, and I'm going to do 2 pi. So it's going to look like that. And then when you hit enter, it's going to automatically translate it to a decimal. Okay, whoops. There we go. Now, x min, we're going to do -3. X max, we're going to do +3. X scale is just going to stay 1. And then y min, we'll do -3. And then we'll do y max, +3. And then y scale, we'll do 1. Okay, so we've kind of set our window. All right. Now, you can go to y equals, and there's already crap in there. Okay, so you can go to y equals, and notice it no longer says y1, y2, y3. It has r1, r2, r3. So we want to type in 1 plus, make sure you're in radians, theta, or what we want 1 plus cosine, and then your theta, you know how like to type in an x, you do this button beside alpha, the xt theta n, it'll now type in a theta, okay? So we have 1 plus cosine theta, and we can go ahead and look at the graph. And there you have it, okay? So notice how our graph is very rectangular, okay? If you want it to look kind of more natural, like what the graph would actually look like, you can go to this zoom button right here. So the zoom button will do different things. It'll go back to the standard viewing window. It'll go to like a statistics kind of thing where you can plot individual points. But for us, we're going to look at zoom square. And it just kind of it makes the graph look a little more natural. Okay. So this we're going to learn in just a second is the graph of a cardioid because it looks like a heart. I've always thought it looks like a butt, but to each their own. I had a heart attack when I saw it because it looked like a butt. But anyway, it's called a cardioid because it looks like a heart. Okay. Now, one other thing I want to show you. You can go to second trace and then choose option one. When you do this, it'll let you type in a value for theta. So you could say, okay, what do I get if I look at theta equals pi over 3? So we could type in pi over 3, and it's going to give you the R and theta value if you do another setting on your calculator. So if when you do this, you get X's and Y's, there's a really quick fix for it. So if you want to, you can go to second zoom. So second zoom goes to this screen and your default is rectangular. So like if I do rectangular, let me go back to that screen really quick. So if I do rectangular and then I go to type in a value for theta like pi over 3, it's going to give me X's and Y's because I'm in like rectangular coordinate. I'm like in the rectangular coordinate grid. But what if I want to see R's and thetas? So again, you go second format and then go to polar grid coordinate and then hit enter. And then when I go back to my graph and I do second trace and I type in a value for theta like pi over 3, then it's going to tell me what my corresponding R is. So R is exactly 1.5 when theta is pi over 3 radians. Okay, so you can check. That's another way you can graph these. You can choose several values for theta and then plug them in or type the equation into the calculator, go second trace, and then you can type in different values for theta and it'll tell you what R is. So let's say we wanted to do pi divided by 4. Well, when we have pi over 4, R is 1.7. When we have 5 pi divided by 6, R is 0.133. Okay, so you can use that to help you create a table. You can also just look at a table. You can go second graph and it's going to give you a theta R table. Okay, now right here, this can be a little bit nasty because, we obviously don't have very many theta values that are integers. So you could go second window and you could have your table start at 0 and then you could increment by pi over 6, for example. And it's going to give you pi over 6 values, but you can't tell they're pi over 6 values because it's all going to be decimals. I don't know if there's a way to convert it where it'll show you like the pi over 6 values, but there you have it. So you can still create a table of values. You can still use the trace button. You can still play with your window. You just have the extra component of dealing with theta now. Okay, so let's go back to our graph really quick. So we have a situation where we're crossing the y-axis at 1 and -1, and then we're crossing the x-axis at 2. So we're going to just kind of sketch this. We're not going to do like a super official graph. We'll just sketch it. So let's go back to the worksheet. And if we go down here, let's sketch. So we had values at 1 and -1 on the y-axis, 2 on the x-axis, and then we kind of had like little heart pieces here. And then, well, pretend that goes through here. Let me fix that. Got a little wacky, didn't I? So let's try that again. All right, so it kind of looks like a heart. It's a little more bulbous on the right-hand side, but you can pretend, okay? So a heart or, rear end, cheeks, whatever you want to see is what you see, but this is an example of a cardioid, okay? So in the next examples, we're going to look at 4 very specific types of graphs, the first being the cardioid. So they do have a very specific format for the equations. They have a very specific shape. We're going to look at 2 examples. We're going to absolutely use the calculator to sketch them. Then we're going to look at the other form, the other special types of graphs, okay?